Okay, so good morning everyone, and today we'll be looking at the topic multimedia. So basically, like technology has improved in such a way, like how we used to transmit audio and video earlier, uh, that has completely changed now. Okay, previously we used to broadcast audio and radio through, maybe you can consider like through TV and etc. We used to send, right? And we use the telephone network to interactively communicate with other party earlier. Okay, if we consider old generation, audio and video, all these things we used to have with telephone network itself. But now things have changed. We want to use internet for audio and video also. Okay, if you just recall, previously we used to do like through internet, we used to do only audio, image and text information transmission. Okay, but when I consider now, we are doing like audio and video are also exchanged through internet. Okay, that is what we do see. Okay, so what is making us to move towards this thing are like things related to sending audio and video through internet. That is what we will be looking into in this particular chapter. Okay. Um, I'm just trying to change my slide. Sometimes we do have some kind of issues with system. Okay, slide changed for you.
Yes, sir.
Okay, so when we consider the audio and video exchange through internet, we can actually categorize into three different categories. Okay, the first one is streaming stored audio video. Then second one is streaming live audio video. Then the last one is interactive audio video. If we talk about the first category, wherein we are saying about streaming of stored audio and video, in this case, we can consider like the files are basically stored in some server. Okay, let us say you have some YouTube. Okay, in YouTube, you might be watching a video, a particular song or movie or any new anything which is not live, I mean to say. Okay, at some point in the past it has been uploaded in YouTube, and you are watching that one today. That is considered to be streaming stored audio and video. Okay, and now what can be done in this case is basically you can download that particular file through internet. Okay, and we can call this thing as on-demand audio or video, because at some point in the past they have uploaded the video, and whenever you are interested, you are trying to get into that particular audio or video. Okay, so examples are like the songs which we watch on YouTube, or maybe some TEDx talk you can consider. Okay, or you can also consider like some you might mostly you might be watching uh, serials, right? So people may be watching serials by downloading them. So all those things we can consider as part of streaming stored audio video. Okay, so next thing is like when we go with the next category, streaming live audio video, then we'll be having like maybe let us say some TV program is coming, or somebody is broadcasting news through internet. Okay, these kind of applications we can consider under second category. Okay, or you can also consider like internet radio. Okay, all these things are considered as streaming live audio video. In the third category, the best example what we can take is whatever we are doing now. Okay, we are having uh, um, a Teams call, right? Okay, it can be audio or video. It can be mix also. So basically, this is interactive, wherein I communicate with you and you will be responding to that. Okay, both way communication. happening here. Okay, it's not a single way. It's not one direction. Okay, so these kind of things we consider as interactive audio video. Okay, clear about the categories?
Yes, sir.
Yes, sir.
Okay, so when we consider the first case, streaming stored audio video, as I told, this is on-demand request for compressed audio video files. Okay, they are stored in compressed manner, and also when you try to download YouTube video or anything, it will ask you what is the quality you are expecting. Even while playing YouTube videos also, you will be given option to select the picture quality, whether you want to go with 720 pixel or 360, 144. Okay, different capacities will be looking, right? So basically they are available in compressed manner, and you can choose whatever the quality you are requesting for. Then when we consider streaming live audio video, it refers to broadcasting of radio and TV programs through internet. The last one, like interactive audio video applications. Okay, so whenever we talk about any of these things, all the three things, we also need to discuss digitizing audio and video. Okay, because for example, let us say I want to send an audio signal or video signal. It's not simply we will be able to send, but they need to be digitized. Okay, because your computer can understand only in the form of zeros and ones. It cannot understand variable voltages or etc. Okay, so especially when we talk about digitizing audio, it is something like we give some sound to microphone, and some electronic signal will be generated. Okay, which is varying in amplitude with respect to time. And if we try to represent that one in the form of digital, most of the cases, voice signals we do consider like the maximum frequency as 4000 hertz, right? You may have considered in your digital communication also. The highest frequency you consider till 4K. Yes or no?
Yes, sir.
Okay, and whenever we try to represent that one in digital, we come across Nyquist theorem. Okay, wherein we say like if the highest frequency is f, and we need to sample the signal at 2f times per second. That is what we have been discussing in digital communication. Okay, if the frequency is, let us say, f, we are going to sample at 2 times f. Okay, so the highest frequency which we considered is 4K. Okay, and when we try to sample that, when we want to go with digitization, we'll be going with is 8K. Okay, 8000 samples per second. That is what we are going to consider with respect to audio, I am saying. And uh, each sample basically we will try to do like we will try to represent with 8 bits. Okay, we are saying highest frequency is 8, so we need to uh, sample at a rate of 4000 samples per second. Okay, and each sample we are considering like we are representing with 8 bits, so overall it will be 64 kilobits per second. Okay, now you should be able to understand why you may have seen a number 64K in your digital communication. Okay, so the digital signal for every second it is generating a data of 64 kilobits. And the same thing if we consider with respect to music, we are going to represent, we are going to generate 44,100 samples per second. Any idea how we are coming across a random number like 44,100? Anybody? No idea how we are coming across with that number?
No, sir.
Okay, so what is the highest frequency we have for audio signals? Range. Do you know voice is different from audio?
Yes, sir.
Okay, so what is the frequency? till which you will be having?
20 hertz to 20,000.
20 hertz to
20,000 hertz.
20,000 or 22K?
20 hertz to 20 kilohertz, sir.
Okay, 20 kilohertz. Okay, so basically we said with respect to Nyquist rate, we are just going with 4K multiply with 2 like that, right? So when we go with music, we are also considering like 20K, and approximately by adding some more bits and extra redundant bits, etc., we are doing like we are sampling at a rate of 44,100 samples per second. Okay. So understood why we are getting 44,100? Yes or no?
Sir,
Yes.
can you repeat it once again, sir?
Sir,
Yeah, tell me.
Can you repeat it once again, sir? How we got 44,100?
Okay. The highest frequency which we are considering is 20,000, right?
Yes, sir.
Okay. So for that, we are adding some more extra things. It's not like directly consider 20,000. Okay. But we are just adding some more bits. Basically, we can go ahead with 40 kilohertz, 40,000 we can go. But according to Nyquist, what we are saying is we can use something which is equal to 2 times the highest frequency or greater than that. Okay, so that is the reason they have chosen like to go with 44,100. Okay.
Yes, sir.
Okay, so this when I consider 44,000, our intention is not with respect to why we are considering 44,100, but our intention is with respect to when I have 44,100 samples per second, and if I represent each sample with 16 bits per second, we will be getting something around 705 kilobits per second. Okay, so basically, with respect to music, you will have two things. One is monaural, other one is stereo. Okay, monaural and stereo. So when I say monaural, only single band information will be sending or single side. Stereo means we'll be sending two times whatever the information we have. So in this case, when I consider 16 bits per second for 44,100 samples, we will be getting around 705 kilobits for monaural and 1.4 Mbps for stereo. Okay, so 7 approximately 700K you can consider. Okay, and the other one is around 1.4 Mbps. This is just for which one? Audio. Okay, you just imagine like we are trying to talk about something which is requesting us to have 1.4 Mbps. Okay, so whether that number is big or small, 1.4 Mbps.
Small, sir.
Small. Okay. Uh, Let me go with video case. Okay. In video, what happens is, let us say, mm, most of the cases, even I may have discussed also. I'm just trying to see if I can insert some text over here. Okay, that's fine. So basically, we call it as 25 frames per second. If you remember, with respect to how we are getting video. Okay, so video, how we are generating is if I move my images 25 images per second, then I get a feeling of video. Okay, so basically in North America and all, they use this 25 frames per second to get a feeling of video. And even we have something called as flickering, uh, because of which we need to refresh the frame twice this particular 25 frames per second. Okay, so basically what they do is they try to send 50 frames per second. Okay, I'm talking about video. So we'll be sending 50 frames per second. Okay, and if I consider like normal resolution of a color image, like we see resolution, right? 1024 by 768. Any idea? 1024 by 768. Uh, we used to consider these resolutions, right? For your
Yes,
screen and
sir.
all. Okay, so if I consider we are sending for 50 frames per second and we are having the resolution of 1024 by 768 pixels, and if I multiply all these things, 50 frames multiplied with 1024 into 768 pixels, I'll get 944 Mbps. Okay, so now tell me the value 944 is very high or small?
Hi, sir.
High. So with respect to audio, we have seen if you are sending speech signal, we are generating at 64 kbps, and if you are sending a music, we might be getting going till 1.4 mbps. But some of you felt like 1.4 mbps is very small. But let me tell you, 1.4 mbps is also a very big number because we are generating per every second. Okay, and see, most of the cases nowadays we are getting this one like uh, somewhere around 50 mbps, 60 mbps, 100 mbps, like that we'll be telling. But when we actually go back and see, we may not be getting that much bandwidth. Okay, especially today also, if you see some of the remote areas, you may not be able to find normal cell towers. Okay, you may not be able to make normal calls also. In that case, if I expect to have some WhatsApp call which is requesting me to have 1.4 mbps, okay, that is very very difficult. Okay, so the overall intention of our discussion is we need to have some compression if I have to send either video or audio over the internet. Okay, because 944 mbps, we cannot just imagine about that. Okay, hardly we are getting 50 mbps or 60 mbps. Even if I consider 5G also, they are talking about speed in 100 megabits, something like that. But we cannot guarantee that with respect to quality of service. Okay, so obviously you can consider when I go with audio or video, we require huge bandwidth. Okay, you are able to understand till that point, right? When we go with audio and video, we require huge bandwidth.
Yes, sir.
Okay, so that is the reason we are going with compression. Most probably in your image processing also, you may have studied about the same thing, right? We want to reduce the amount of data which we are sending. So that's the reason we are going for compression. Yes or no?
Yes, sir.
Okay, so let us see how exactly we can do compression with respect to audio and video. I don't know if you have looked into these things in your image processing or not. Maybe you may have concentrated only on images, right? Not on audio and video.
Yes,
Yes,
sir.
sir.
Okay, so there was a subject image and video processing. In that, basically they talk about video compression, etc. Okay, anyway, not an issue. So when I consider audio compression, basically where we are trying to send a speech or music signal, we said like we require 64 kilohertz or 64 kbps for audio and 1.4 megahertz for music, like that we consider, right? So we have two things here, predictive encoding and perpetual encoding in the case of audio. Okay, so predictive encoding means basically what we will be doing is the difference between the samples are encoded instead of encoding all the sample values. Okay, so let me write here. Let us say the values are like this, 24. Okay, and then I have next sample value is 32. Okay, next sample value I have is 26. Let us say. Okay, next sample value, let us say I have some 16. Next sample, let us say I have 30. Okay, so these are the values I have, let us say. And if we consider the difference, okay, let me take the first value as it is 24. Next, what is the difference I have? 8. Next, what is the difference I have? 6. Next, I have a difference of 10. Next, I have a difference of 14. Okay, you try to imagine if I have to represent a number 32, how many bits I require? If I have to represent a number 8, how many bits I require? There is a difference or not?
Yes, sir.
Okay, so as the number is growing bigger, we will have to represent with more number of bits. Okay, that point we are actually taking into consideration. Okay, so what we are doing in predictive coding is instead of sending the values as it is, we are trying to consider the difference values, difference of samples, so that some of the bits we can reduce. So basically in GSM we use that GSM 13 kbps, G.729, wherein we go with 8 kbps. Okay, you can just imagine we were talking about 64 kbps, but we almost reached to 13 kbps and 8 kbps. Okay, so lot of compression we have done. Okay, that is with respect to predictive coding, wherein we are talking with respect to the difference of samples. Okay, next we have something called as perpetual coding, perceptual, not perpetual, perceptual. Okay, in perceptual coding, basically we try to consider psychoacoustics of user. Okay, so what is this psychoacoustics of user is, for example, let us say, uh, see, most of the times we do experience in our college also, wherein some event is going on or flash mob is there or nearby, let us say the school near to us, from there is an event. Okay, what happens is if they are playing the music or anything with loud sound, then if somebody is murmuring near you, you won't be able to hear that, right?
Yes, sir.
Okay, so that is considered to be masking actually. Okay, so what happens is here a loud sound in a frequency range can partially or completely mask a softer sound in another frequency range. Okay, so the loud sound which we are getting, especially let us say you are having annual day celebrations and we are playing some music over there. And if somebody is trying to talk in phone, they won't be able to hear. Okay, they'll be able to hear only the DJ sound. It's because the loud sound in a particular frequency can partially or totally mask softer sound in another frequency. Okay. Then another case is like, for example, somebody tries to play some big sound, okay, loud sound, let us say, okay. After you hear that, for some duration, your ears will not be able to respond to sounds which are very, very small. Okay, we are telling with respect to frequency, we are telling with respect to time also. Okay, with respect to frequency, what we are saying is loud sound is trying to mask softer sound. Okay, and with respect to time, what we are saying is whenever we hear a loud sound for a small duration of time, I won't be able to hear any smaller sound. Okay, are you with me so far? Like whatever I am saying.
Yes, sir.
Okay, so one is called frequency masking, other one is called temporal masking. So any one of these things, if we have, we don't have to consider like, for example, we have a loud sound and soft sound. In that case, I won't be able to hear soft sound, right? So there is no point in sharing that information. Okay, the soft signal. Okay, and a loud sound is there which is masking our ears for some duration, and we are not able to hear the soft sound immediately after that. In that case, for that small duration, I don't have to consider the soft sound also. Okay, so by considering these two things, frequency masking and temporal masking, if we are doing some compression, that is considered to be perceptual encoding, which we do in MP3. Okay, understood what we are trying to say?
Yes, sir.
Okay,
Yes,
so next thing we are going with is video compression. So video compression basically we cannot directly say like it's a separate thing which we are considering, but we need to consider first image compression, then we will have to go with video compression. Okay, so the famous thing JPEG, anybody can say the expansion of that? No idea? You may have studied this one in your image processing, right?
Joint
JPEG.
Photographic Experts Group.
Exactly. So JPEG stands for Joint Photographic Experts Group. And when we go with video, we call it as MPEG, which stands for Motion
Moving Picture.
Moving Pictures Expert Group. Anything, Motion Picture Experts Group or Moving Picture Experts Group. Okay. So basically, we'll try to look at JPEG and try to understand how it is happening. Then we'll move our discussion to MPEG. Okay. So JPEG, basically what we do is take the entire image, try to divide the image into smaller subblocks like this. Okay, 8 by 8 subblocks, whatever we are able to see here. Okay, or 8 by 8 pixels we are considering, let us say. And we are trying to give that blocked image to DCT, okay, discrete cosine transform. Then we are going with quantization. Then we are going with data compression and we'll be getting compressed image. Okay, so what happens in this one is we try to do discrete cosine transform. What does this discrete cosine transform do is it tries to come up with averages. Okay, average values like DC value we can say, and we will also get some AC values. Okay, so basically we will be getting total 64 values for the 8 by 8 subblock which we are considering. Okay, so when I do this discrete cosine transform, we can consider like this. For example, if I have uniform grayscale image, which is having same information for the entire image, and if I try to give it to DCT, it will be giving me this particular block. Okay, wherein you can see I have just one average value 160 and 63 other values are zeros. Okay, so now you just tell me like instead of sending 6420 values, I can just send 160 and I can say like 63 zeros. Okay, so drastic decrease will be there with respect to the number of bits which we are sending. Okay, that is one case. When I consider case two, wherein I have two sections, let us say here also you can see we have only 5 non-zero entries. Okay, even if I consider gradually varying image like this, I can see like around 7 non-zero values I have. Okay, so that is the beauty of this discrete cosine transform. Okay, so it tries to concentrate more values at lower frequency ranges. Okay, and we won't be having most of the higher frequencies we'll be having as zeros itself. Okay, so that is what we are considering from discrete cosine transform. And whenever we are doing like we'll be doing even quantization. Quantization also it will be like we'll have a matrix of 64 bit like 8 by 8 matrix. Okay, in that also each entry, like if I consider 1 comma 1, that is first row first column, first row second column, first row third column, second row first column, second row second column, second row third column, like that each and everything will be undergoing different quantization. Okay, we will have some entries here, and quantization how we are doing is take the output of DCT and just divide with whatever the value we have in that quantization matrix. Okay, so each and every entry in the output of DCT is going to experience different quantization levels. Okay, then what we are doing is we are going with this one. Okay, when we are reading also, we are not reading continuously line by line or row by row, something like that, but we are using this zigzag pattern. The reason is when I go with this zigzag pattern, after a certain point, like let us say after 12, okay, you can see all are zeros. Okay, so there we will be using something called as run length coding, RLE we call it as, wherein whenever you have continuous zeros, we will be just writing like 0 comma 6, which represent zeros are repeated for 6 times. 0 comma 50, zeros are repeated for 50 times. Okay, so you can just imagine the result whatever we have after JPEG compression. So almost we have reduced from 64 So are you able to hear me?
Yes, sir.
Okay, so the famous power cut is back and okay. So we were discussing like when I undergo all these stages like which we have seen in JPEG, DCT, quantization, data compression, etc. At the end, I am going to get only these things, right? So that is what we are getting with JPEG. Okay, so understood how JPEG, like what exactly we are getting in JPEG.
Yes, sir.
Okay, so next I will move our discussion to MPEG, where we do talk about these frames. Okay, so MPEG, we said like it's not just one frame which we are sending, like in the case of video, but we will be sending multiple frames, right? So multiple frames, what we will be doing is we will be dividing into three categories of frames. Okay, so the three categories of frames are iframe. Next we have P frame, then we have B frame. Okay, so basically when we go with JPEG, what we have done is we have considered spatial redundancy. Okay, so any idea what is that spatial redundancy? I'm trying to consider a frame. Okay, I have a particular value over here, and I'm trying to compare that value with neighboring pixels. Okay, so if complete image is, let us say, a hilly area, okay, or if complete image is just a sky which we are able to see, in that case we won't see much variation with respect to one pixel and other pixel. Uh, do you agree with that point?
Yes, sir.
Yes, sir.
Okay, so in that case, I don't have to send each and every pixel value. Okay, I can just remove the redundancy in that case. Okay, so for example, in a particular location with respect to probability also we talk, right? Daily it will be raining here, then there is no information which we are sending. Okay, but if the probability value is more, okay, lot of variations we are going to have, then we can say like lot of information I am exchanging in that case. Okay, so basically here also spatial redundancy means within the frame how things are getting changed. That is what we are considering. And when I say temporal redundancy, I'm talking about one frame to other frame. What are the changes I'm going to have? Okay, to make you understand in better way, let us consider another frame. Let us say you are moving in front of our block, library block we have, right? Okay, so somebody is trying to take that video by standing in front of open auditorium. Okay, so what will be there in the frame? Like you will have the library block in front of which only you, let us say, only you are there, nobody else are there. So you are moving. So in the frame, you'll be having the block, the trees, and a particular person moving from one location to other location. Okay. Now we said when I consider video, this is something like multiple frames we are considering per second, right? So when I consider first frame and second frame, what is the difference you are going to have? Any idea? Or let us say multiple images. Okay, video is like continuous images itself, right? When I take the first image and second image, the image which is there at let us say 100 and the image which is there at 100 point some 50 microseconds, 50 seconds, what will be the variation? That is what I am asking. Entire background will be same and only the person will be moving some pixels ahead. Yes or no?
Yes, sir.
Everybody understood what I'm trying to say?
Yes, sir.
Okay, so when I consider like somebody is moving from one point to another point, and if I see the successive frames, Entire background will be same, but only the particular person will be moving from one location to other location. Okay. Now tell me, whenever I am transmitting this information, is there any need of sending the background information again and again?
No, sir.
No, because already I have that information in the first one. I just need to say what is the variation. Okay. So even with respect to like wireless sensor network, we do consider that, right? Let us say, like we are monitoring a particular location. If it is giving constant values, I don't have to talk about it much. Only when there is a variation, then only I need to talk about it. Okay. So we are considering two things here, spatial redundancy and temporal redundancy. And if we remove these two things, we call it as spatial compression and temporal compression. Okay. So especially in iframe, what we do is, this is called as intra-coded frame or independent frame also we can call it as. Okay. So this is not related to any other frame. Okay. Whenever we are talking about this first iframe and the last iframe, we are not linking that one with any other frame. Okay. We are just looking with respect to what spatial redundancy we have in that one. Clear, right? What I am saying? Next, when we move with P frame, this is called as predicted frame. Okay. And this P frame is predicted from previous I frame or P frame. Okay. Let us say this P frame is there. It will be predicted by taking the reference from I frame. Okay. Or if I have a sequence of P here, in that case, I'll be having a prediction from previous P frame. Okay. But when I go with B, which is called as bidirectional frame, this is related to, let us say this B frame is there. This will be linked with this I frame, and also we will have a link with P frame. Okay. So I frame, we are not linking with any other frame. P frame preceding I or P frame from which we are taking the reference. B frame, we are taking both I and P frame. Okay, preceding and successive, both frames we are trying to consider as reference. Okay, so reference, I mean to say, taking into reference is these two things. Whatever the difference we have, that we are going to encode. Okay, understood, right? What we are saying? You can see here how we are taking the reference. I frame directly we are taking. P frame we are taking the reference from I and P. P frame we are just taking from I and the corresponding thing, whatever we have. Okay, like that we are taking the reference. Like that we will be taking the reference and we will reduce spatial and temporal redundancy. That is how we are achieving compression with respect to MPEG. Okay, clear this thing also?
So the order of the frames must be in the same as it is displayed, or it can be in any order, sir.
Exactly. You need to have an I frame. After that, I can have B frames. Then I can go with P frame. Okay. Again, I'll be having B. Again, I'll be having I. The reason why, like you can ask, I can have only one I frame and consecutive B and P frames like that. But the thing is, uh, let us say a video has started now. Okay, live video. Somebody after 10 seconds they are logging in. They won't be having iframe to take the reference back, right? So for that reason, what we will do is these iframes will be repeated multiple times so that there will be a point of reference for them to go ahead with. Okay. And order in the sense, maybe I can have 3 B frames in between rather than 2, something like that. But we'll be having iframes, B frames, P frames. Okay.
There is B frame called as a
Okay.
successive frame, sir.
It is called as bidirectional frame.
Okay, sir. So that means the B frame is dependent on I, B, and P.
Exactly. Okay, for this B frame, we are taking the reference from I and also P, and we will also be comparing what values we have here, right? Our values, like which we have in this, I'm going to take a reference from I, and also I'm going to take from this P value. Okay.
Yes, sir.
Clear for everyone?
Yes, sir.
Okay. So we will stop here, and in the next class we will discuss about audio on demand, all those things.